In 5.2 Part B, we're going to be looking at elimination as the technique for solving systems. In elimination, I want to choose a variable to eliminate, and usually identify the lowest common multiple, find the smallest one of those, and that helps me figure out which one I can get rid of most easily. Then I need to multiply each equation by whatever number is required to create the least common multiple, and the opposite of the least common multiple in the other, so one positive, one negative. Then we'll add the two equations together. That's going to allow us to get an answer for either x or y. Then I substitute the value of the one I find to find the value of the other. Okay. So what I look at first is my x's and my y's, and I try to find which one has the smallest least common multiple. For example, the least common multiple between 4 and 3 would be 12, and 2 and 1 would be 2. So y has the smallest least common multiple. So we're going to use the y's with an LCM least common multiple of 2. That's the smallest. Just for reference, the x's would have been 12, so we're going to go for the y's. Okay. Now, there's already a negative 2 on the top one, so I don't need to change that. I just need to make the bottom equation have the opposite, so a positive 2. So we're going to multiply this entire equation by 2. Okay. We'll leave the top equation alone. I like to write my top equation first. So 3x minus 2y equals 8. And then we're going to distribute that 2 into the bottom equation. So the bottom equation is going to become 2 times 4 is 8x plus 2 times y is 2y equals 2 times 7 is 14. Now we add the two equations together. 3x plus 8x is 11x. This is where the name elimination comes in, because negative 2y plus 2y adds to 0y. They eliminate. And then I have the 8 plus 14 adding to 22. And we can continue to solve by dividing both sides by 11. That gives us x equals 2. Once I have the value for x, I'm going to take it into either original equation, plug in 2 for x, and solve for y. Let's go with the top equation here. So that's 3x, or 3 times 2, minus 2y equals 8, or 6 minus 2y equals 8. If I subtract my 6 from both sides, that's negative 2y equals 2. And dividing that negative 2 from both sides gives us y equals negative 1. Don't forget to take your two solutions for the x and the y and put them back into one ordered pair. So the solution to the system is that these lines intersect at the ordered pair 2, negative 1. Let's take another look in example 4 and use the elimination method again. For the x's, the least common multiple between 9 and 12 will be, the multiples of 12, 24, 36. I think it's going to be 36. And for the y's, between 6 and 8, it's going to be 24. So this time, just because it's a smaller number, it makes things a little easier. We're going to go with the y's. We're going to eliminate the y's. Actually, again, I guess we did it last time too, just by coincidence, because they have the smaller least common multiple. Now, this time I do need to multiply both equations by something. I can multiply the top equation by a 4, because 6 times 4 is 24. That's going to create a negative 24, so I must create a positive 24 in the next equation, and they need to be opposites. So I need not just a 3, but a negative 3 to turn that negative 8 into a positive 24. Okay, we're going to distribute these all the way across their equation. 4 times 9 is 36x, minus 4 times 6 is 24y, equals 4 times 15 is 60. Most common mistake is to forget to distribute the 4 all the way to the other side. All 3 terms are going to be distributed across. Now I have to do the negative 3 times each of them. Negative 3 times 12 is negative 36x. Negative 3 times negative 8 is positive 24y. And negative 3 times negative 20 is negative 60. When I add these together, I do eliminate the y's like we intended, but I also, unintentionally, coincidentally, eliminate the x's. There's nothing left on this side at all besides 0 equals 60 minus 60 is also 0. Okay. Just like in the first part A, we had one example where we had an intersecting system. Oopsie, forgot some letters there. There we go. Intersecting system. And that's just an example of how it might work if we have a single solution. Down here, let me move my mouse out of the way. Down here, I have a case where my variables have disappeared. They have eliminated each other, so we're not intersecting. Whether or not this is true or false is going to determine if I'm a parallel or for an identity. Here, it's true, so that means that this must be an identity. So that means that my answer is all points on the line. Usually we answer in y equals form. I don't know y equals form yet, so I'm going to solve one of those for y. Let's take the 9x minus 6y equals 15 and solve that for y. We'll subtract the 9x from both sides. Gives us negative 6y equals negative 9x plus 15. And we're going to divide every piece by that negative 6, giving us y equals, if I reduce 9 6, it's 3 halves, 2 negatives made that positive. And the negative, if I reduce by 3, that's going to be negative 5 halves. Okay, so my solution, which I haven't written down yet, is all points on the line y equals 3 halves x minus 5 halves. Had I solved the bottom equation instead of the top, I would have gotten the exact same y equals form, because those two forms are just unsimplified versions of the same thing. So all points that lie on that line will be solutions to that system, since the two lines are equal.